Okay, so this week we will be focusing on regression and regression trees. In general, the goal of regression is to use one or more independent variables to predict a dependent variable. We want to understand how the dependent variable changes when we vary an independent variable while holding all other variables fixed. There are many forms of regression, but the most widely used is linear regression. In simple linear regression, we fit a line based on minimizing the squared error from each data point. This is called ordinary least squares regression. However, there are other forms of regression, such as partial least squares regression, where our goal is to project the variables onto latent structures. We can also try to fit nonlinear functions to data with the use of polynomial functions. While linear regression has sufficed for many applications, there are many others where it fails to perform adequately. Just to illustrate this point with a simple example, shown here is some noisy data for which linear regression yields the line shown in red. The blue line is the output of the tree regression algorithm that is presented in the second half of this lecture. Which algorithm do you think does a better predictive job? Linear regression creates an estimate about the mean value of the dependent variable based on the independent variable, and as noted, the function that we fit through our estimate does not have to be linear. We have our dependent variable y and the coefficients alpha 1, alpha 2, etc., and our parameter estimates that will tell us how much y varies based on an increase or decrease of each of the x variables. First example is a typical multiple regression function, and the second example shows the additions of increasing the power of a variable to create a polynomial function. When we interpret the output of our regression analysis, we pay close attention to the statistical significance and the coefficients produced. The p-values indicate whether the values are statistically significant, and the coefficients describe the mathematical relationship between each independent variable and the dependent variable. P-values less than 0.05 are typically used to determine statistical significance. But what this test is actually saying is about the likelihood of finding a more extreme value. With respect to hypothesis testing, when we run a linear regression model, the p-value just tells us whether the correlation between our dependent variable and our independent variable is not zero. Often, too much weight is given to the value of statistical significance. In essence, we are just verifying that the independent variable is associated with the dependent variable. Thus, statistically significant variables should remain in our model. The coefficients provide more detail about the relationship between the dependent and independent variable. The sign of the coefficient tells us whether there is a negative or positive correlation between the variables. And sometimes with our data, we have to adjust the sign of our coefficient in order to make sure that correlation stays correct. An example is when asking a survey question, sometimes we have to flip the order to make sure that the responses better correlate to our dependent variable. What I mean by this is in a Likert scale survey, when we have answers 1 through 5, where 1 is not likely and 5 is very likely, depending on the orientation of the question and what our expected response is, sometimes in our data we have to go through and flip all those values around to make sure we keep the proper correlation. But really, the most important part of the coefficient and part of linear regression analysis is to understand how to interpret the coefficients. And with that, what we need to say is that with a 1 unit increase in an independent variable, we will see the amount of that independent variable's coefficient increase in the mean value of the dependent variable, assuming we hold all the other variables fixed. With regression trees, they are useful to talk about as they allow a piecewise function, linear function, to be fitted to the data. However, after we demonstrate how to perform a regression tree, we will talk more about the strengths and weaknesses of this analysis. In R, we will use the rpart package to do the regression tree analysis. Another package is rpart.plot, which allows us to visualize the decision tree. In this example, we're going to use the Ames housing data to analyze the effects on housing prices with variables such as the year it was built and square footage. We're first going to split our data into a 70-30 train and test set. We set a random number, and then we use that to randomly split our data into 70-30. This creates our training set and our test set. We then use rpart to create a function for our regression tree analysis. We're going to assign it to M1. The formula, we're going to try to predict the sale price based on all the other variables in this data set. We're going to do it on our training set, and we're going to use method ANOVA, which indicates that it is a regression tree as opposed to a classification tree. After we run the model, we can examine how the algorithm splits the data. However, it is not exactly easy to see, but we can see that the first variable it makes a split on is overall quality. But it's easier to examine regression trees if we use the rpart.plot to visualize it. This is what the decision tree looks like on this set of data. You can see that the algorithm first splits the data based on overall quality here. Then, if the overall quality is very good, it further splits it into ground living area, then to the neighborhood, and finally the total basement square feet. And then the other side of the tree is done the same way. We can examine the output of the model, or the output of the model can be examined through a function called printCP. And CP is the complexity parameter, which is used to control the size of the decision tree and select the optimal tree size. The second thing is that will give us the number of splits, and the splits are decided based on minimizing the sum of squared error. algorithm decides on the number of splits and which variables provide the best analysis. Here we can see that 5 variables were decided on here. First floor square footage, ground living area, latitude, neighborhood, overall quality, total basement square footage. 6 variables. We see our CP table here, and based on the complexity parameter, we see how each split occurs and the number of relative error that we're able to reduce. So after the first split, we've reduced our error by almost half, but then each of the other splits slowly reduces the error. Our part uses something called a greedy algorithm to split the data, meaning that it will not revert a previous part of the tree based on future splits. The goal is to reduce the error as much as possible at each split. So our part uses a cost complexity alpha value to prune the tree, and a 10-fold cross-validation is performed to validate the alpha value on the holdout set, or the test data we separated out earlier. We can do manual tuning of the algorithm by using these functions min, split, and max step. Basically what those do is allow us to control the minimum number of splits in our decision tree, as well as the max depth, which is the number of internal nodes between our root node, where we start, and our terminal node, which is where we end. When we want to examine our predictive power, we will use the caret package. Bagging, which is a kind of bootstrap aggregation, allows us to reduce the variance in our decision tree. We will make our prediction on the test set of data and examine the root mean square error to determine our prediction accuracy. You can see after this that we will be able to get within $35,000 of the actual price of house with our model. We first set up our cross-validation, and then we run our bagging model. This model takes a little bit longer to run. Okay, you can see the summary of our results by looking at our assigned function. And based on our root mean squared error, we can see that based on the price, we can predict within about 35,000 of, or 37,000 here, of the actual house price based on how we split our data. We can look at plot of the most important variables. We can see that the ground living area is the most important variable to predicting our prices based on the variables that we have. Secondly, we have total basement square footage and first floor square footage, etc. This is the variable importance function for our model. Okay, so we run our predictive model on our test set, and we can see that when we actually test the model, the predict is part of the caret package. When we actually test the model, we see that our root mean square error is actually reduced to 31,850. So it's actually closer to $32,000 off of. We can predict a house's price with but will be about $32,000 off of the actual value. So some strengths of regression trees are that for the most part, they're pretty easy to use. They're easy to follow if you look at the plot of the decision tree, so you can see how the variables are split. If we have missing data, we can average different leaf nodes together without losing too much accuracy. However, this is probably the most important part. The weakness of regression trees is that a single regression trees have high variance and in practice are not very accurate in their predictions. It is important to understand regression trees though, because it is a precursor to the random forest algorithms, which are significantly more powerful, and we will cover random forests later in this class.